Hello everybody. Today we will be solving Leetcode 2097, valid arrangement of pairs. So they provide us a pairs list which has a sublist of 5, 1, 4, 5, 11, 9, 9, and 4. What they are essentially asking us is they want us to return an arrangement so that the ending value of a node or a pair is the starting value. So notice how 9 is the ending value here, but it's also the starting value for this pair. The ending value of this pair is 4, and that's the same as the starting value here for this node, which is 4. This is the value, ending value is 5 over here, and the starting value is 5. So this is the answer for this problem. In this problem, again, they give us a pairs listing, and notice how 1, it doesn't matter about 1 here because it's the first node, but this ending value here is the same as this 3 here. Start is the same as this, sorry, this ending value of 2 is the start of this 2, so this is fine. But notice how they also give other possible arrangements that would have been worked. Okay, so for this problem, we'll be using a somewhat unknown, or if you're familiar with graph theory, then it is known, a algorithm by the name of Hierholzer's algorithm. Okay, let's start with this problem here, and let's learn something. So what I've done here is I've just written down this first example. They tell us that 5, let me just go back in case we've forgotten. So notice how 5 can go to 1, 4 goes to 5, 11 to 9, 9 to 4. I've just written it in these terms. So let me just write that down, right? Or maybe I want us to help visualize. I want to help us visualize this better. So 5 to 1, that means 5 can travel to 1. 4 goes to 5, okay. Okay. 11 goes to 9. 11 goes to 9. Okay. It doesn't matter for now, but and then they tell us 9 goes to 4, so I can move that up here. Okay, so all I've done is just expand what this means. 11 goes to 9, 9 goes to 4, 4 goes to 5, 5 goes to 1. Now, I want us to develop some intuition here. Notice that the degree of 9 has an out degree of 1, but then it has an incoming degree. So the net degree would be 0. Same thing for 4. It has an incoming degree of 1. Sorry, well, in essence, maybe -1. And when it goes out, we can call that +1. So the net degree is 0. Same thing for 5. Notice how 1 has so we'll call this here maybe, so incoming, we'll call this maybe a -1. And outgoing, we'll call it +1. So notice here that 11 is the only node with an outgoing degree of 1. So if we're developing intuition here, it would make some sort of sense that this, whatever node has an outgoing degree of 1, would be the starting node. So I want us to understand that. It should make sense that whenever you have a graph and you're attempting to solve a problem like this, find a path, that we should start with the node which has an outgoing degree of 1. Okay, so I wanted to make that clear before we get started with the Hierholzer's algorithm. So I've written down the pseudocode for it right here. Sorry, but let me also go over this example here. I think this will be good. So let me go over this here. So before I go over Hierholzer's algorithm, so let me just write that down. Hierholzer's algorithm. So before I go over Hierholzer's algorithm, I want to just go over this example real quick as well. So 1 goes to 3, 3 goes to 2, and 2 goes to 1. So let's expand that out a little bit just to visualize it more. So 1 goes to 3, 3 goes to 2, and 2 in essence goes to 1. So I need to, I'm not sure how to do that here, but without visualization, let me just try this here. So if I do this, maybe this, and maybe, and then we'll just draw this back, maybe something like this, and then maybe an up arrow here, and then put this. Okay, let's try that. Okay, cool. So 1 goes to 3, which is here. 3 goes to 2, which is here. And then 2 goes to 1. Okay. So now let's look at the degrees as we did over here before. So the degree of 1, well, it has an outgoing degree, which is 1, and then an incoming degree. So that would make the net degree, like the total combining in and out, would be 0. And then for 2 again, the incoming degree would be -1, and then outgoing would be +1. So again, that would be 0. And same thing for 3. So it has, if we're looking at this problem as opposed to this one, it was somewhat easy because we knew when we saw the node with net degree of 1, we knew that was the starting node. But for this problem, it turns out that it doesn't matter which node we start with. That's why, if you notice for here, the answer was 1, but notice how if you start with 2, it also works, and if you start with 3, it also works. So I wanted to make that point. So whenever we have a degree with 1, that will be the starting node. Whenever we have a node with when there is no node with a net degree of 1, we can start with any node and that'll be perfectly fine, and we can arrive at our answer. Okay, great. I just want to make sure we understand that before we move on. Okay, fine. Now let's move on to Hierholzer's algorithm. So the way it works here is, let me just maybe copy this really quickly so we can visualize it here, or walk through an example. So for this example, remember, we saw that the 11 was the only node that had a degree of 1, a net degree. So we would start with that one. So in essence, we'd be substituting. So find Euler path of, we'll call it 11 for now. And we'll want to store our path here. So the algorithm states that we loop through all the neighbors of this node here. So the only neighbor of 11 is 9. So let me see. So u will be 9 in this case. U equals 9. We remove u as a neighbor of v. So now in our graph here, let me just update it. So now this doesn't exist. Let me see. Let me just make it. What can we put here? We'll just call it. We'll just make it empty. I'll do that. It's empty. Remove u as a neighbor of v. Then find the Euler path of 9. find Euler path of 9. Okay, then we go into this again, and it says, in this case, 9 is V, and what are the neighbors of 9? 9 has a neighbor of 4, okay, so in this case, U is 4, and we find the Euler path of 4. Find okay, and then, sorry, what I forgot to do is remove this here. Okay, so find the Euler path or Euler path of 4. So 4 has a neighbor of 5, so that means in this case U equals 5, and now remove this here, and now we find the Euler path of go here. Okay, of 5. Okay, then we go into here. 5 has a neighbor of 1. Okay, so in this case, U equals 1, and then we find the Euler path of 1. Okay, so we remove 5 is no longer a neighbor of 1. Sorry, 1 is no longer a neighbor of 5. Okay, and then we go into using this algorithm here. We iterate through all the neighbors of 1, but notice here how 1 has no neighbors. So 1 has no neighbors, which means we can go back up the stack, and we can add vertex V to the path. So again, since there were no neighbors of 1, we can add vertex V to the path. So in this case, at this point, V is 1. So that means at this point, the path has the value 1 in it. Okay, then we go back up. So now we're back up here at 5. We ask, remember, we're supposed to loop through all the neighbors of 5. 5 has no more neighbors, which means we can go to step 2, which means we add vertex V to the path, which means we add a 5 here. And same thing up here. We go back up here to 9 now. So we're at, yeah, sorry. Yeah, so 9, where are we at? Sorry. No, sorry, we were here, now we're here, sorry. Okay. So 4, the neighbors of 4, we had visited 5, but now 4 has no more neighbors, so that means we're done, so we can go finish this, and we can just, carry on all the way up the stack. And we'd be done with the algorithm, and we'd have our path in essence. Now notice how we'll have to perform some manipulation to make this look like this here. And it shouldn't be too hard. Notice how it's kind of 11.9 is this here, 9.4, 4.5. It's close to what we want, but we'll just perform some manipulation and we should be fine. And that's the essence of the algorithm, and we should be good enough to get started. Notice how I use the neighbors here. So we'll be storing the neighbors in a default dict, and also we'll use the degree. Remember, because we needed the degrees to figure out where to start. When we have a net degree value of 1, that's the node to start with. All right, so let's get started. Let me just clear this out of the way for a moment. All right, cool. So we'll store the degrees and the graph. So G and D equals default dict, and we'll call this, doesn't matter, we can list, and default dict. And this will be for storing the degrees, the net degrees. Okay, so let's loop through the pairs. Okay, so I've added V as a neighbor of U. Okay, and now for the degrees, we'll have D of U. So that means we're going from U to V, and we'll call this plus 1, but d of v, we'll call this minus equals 1. Okay, great. Now what we'll do is we'll figure out which node has a degree of 1. And if there isn't one, it doesn't matter. We'll just start with any node then. So let's do that. So for node in D, if D of node equals 1, then break. That means that once we break, this node will be that whatever node that has the degree, a net degree of 1. If there is no node with a net degree of 1, then that means this node will be the last node, which is perfectly fine. It doesn't matter which node it is. It'll be just any node, the last node that we loop through. This will exist after this for loop. That's just the way Python works. So it's a little bit of a, I don't want to say a trick, but an understanding of Python. If you had tried this in another language, like for example, Go, it probably would not have worked. It will not work. Well, it depends how you set it up. All right, so let's continue on. So we'll set up our path here, and we'll set up this maybe function. We'll just call this, instead of find Euler path, we'll call it DFS. And we'll pass in a node. And while this node has neighbors, we'll call well, let's do a couple things. We'll make it a little bit more clear here. So g of node dot pop. So this will be a neighbor, and then we'll perform DFS on this neighbor, which is essentially what we have here. That's why I have this indentation to indicate a recursive approach. Once we're done with that, we can, according to step 2 here, once we're done, once there are no more neighbors, we can add that vertex to the path. So while there's no more neighbors, we can add it to the path. So let's do path dot append that node, and we'll need to call this. So here this would have been 1. So sorry, it would have been the node with either degree 1 or any node, which is fine. And what's going to happen is this path is going to look something like this here. What is it? What did we have here? It would look something like this. So we want to perform some manipulation so that we look something like this here. 11,994. So let's perform some looping manipulation. So we'll start at the last one and we'll loop forward, and we'll take 2 at a time. So let's do that. So we'll do for I in range, and we'll start at the back. So length of pairs. So length of pairs here. So notice how there's 4 pairs. 1, 2, 3, 4. So that's what we want, 4. And we'll make this -1. And we can do something like so we're starting here and we want to go back 1. We want to go back 1 index. So path I minus 1. And then we can return this, and this should work. Let's test it. Did I forget it? There's a lot of brackets here. I want to make sure I don't forget any. So this is that. All right, this should work. Did I spell something wrong? Okay, default. Okay. Okay, great. Looks like it works. What I'm going to do though, this is, I think it should pass. What I'm going to do is add a slight improvement here. It does pass, but let's go over what we can do better. So that it works fine. So let's move on. So one thing that I kind of don't like is that if we can fix this so we already have the results formatted as we need them. So what we can do here is I can move this here, and instead of appending the node, I'm also going to add the neighbor as well. So let me just show you what I mean by that. So here was path.append. I'm going to append the node and the neighbor. Okay. In this case, this will give us our answer. Sorry, I need to add a tuple here. But let me just print this out for the moment. Print path. And I'm just gonna, that's fine. I'm just gonna leave it like that for now and maybe just return the path. I want us to see what it looks like. So the path, this is what we have, 11.9. So notice how it's exactly the reverse, 11.9, 11.9. This is what they want, 9.4, 9.4, 4.5. We can just reverse it. And that was because the way that we're adding it to the path. So remember, in this case, we're adding 5 and 1, which is what we had here, 5 and 1. But remember, we're adding it to the path backwards. So all we need to do is just reverse it. And then we should be good to go. So it works fine. And let's submit it. Okay, so it's beautiful now. All right. That should be it. I think the problem originated because a gentleman by the name of Leonard Euler was asked, he was asked if you can visit 7 bridges in Königsberg exactly once. And he provided a proof that said you could do it. But he didn't provide the algorithm for how to do it. And that's where Hierholzer came into play. So Leonard Euler said you could do it, whereas Hierholzer stated how to do it. That's just the gist of the history of this problem. Leonard Euler is considered the founder of this branch of mathematics called graph theory. So I think this problem was the first problem that started the whole branch of mathematics off. Okay, if you have any other questions or if this was educational or helpful, give a like or subscribe. Other than that, have a great day. Take care.